Non-constructive proofs. If there are balls in a box and we know that the probability that a randomly selected ball is blue is more than zero, then we can certainly conclude that there is at least one blue ball in the box. This thought seems utterly simple at first sight, but it has proved to be extremely useful in existence proofs, as the following examples show. Recall that in chapter 13, we defined the symmetric Ramsey number R of kk. For easy reference, this was the smallest positive integer, so that if we two-color the edges of the complete graph on R of kk vertices, we always get a kk subgraph whose edges are all the same color. Now we are going to find a lower bound for RKK by proving that R of kk is greater than 2 to the k over 2. Let us take a closer look at the statement to be proved. What it says is that if G is a complete graph on 2 to the k over 2 vertices, then it is possible to color the edges of G so that no monochromatic copy of kk is formed. When we proved similar statements in chapter 13, showing that R of 33 is greater than 5, or R of 44 is greater than 17, we proved them by actually providing a coloring of K5 or K17 that indeed did not contain the required monochromatic copies. However, this was more than what we strictly needed to do. To prove R of kk is greater than 2 to the k over 2, it suffices to prove that it is possible to color the edges of G so that no monochromatic copy of kk is formed. It is not necessary to actually find such a coloring. We will shortly see how big a difference this is. Theorem 15.5. For all possible integers k which is greater than or equals to 3, the inequality R of kk is greater than 2 to the k over 2 holds. Prove let G equals to Kn, and let us color each h of G red or blue as follows. For each h, flip a coin. If we get a head, we color that h red, otherwise we color that h blue. This way each h will be red with probability 1/2 and blue with probability 1/2. We are going to show that the probability p that we get no monochromatic kk subgraphs in G this way is more than 0. On the other hand, p is equals to the absolute values of f divided by the absolute values of omega, the number of favorable outcomes divided by the number of all outcomes, where omega is the set of all possible two colorings of the edges of a complete graph on n vertices. So p is greater than 0 implies that there is at least one favorable outcome, that is, there is at least one kn with two colored edges that does not contain any monochromatic k4 subgraphs. Instead of proving that p is greater than 0, we will prove that 1 minus p is less than 1, which is an equivalent statement. Note that 1 minus p is the probability that we get at least one monochromatic subgraph in our randomly colored graph G equals to Kn. The number of ways to color the edges of a given kk subgraph of Kn is clearly 2 to the k choose 2, as there are two choices for the color of each h. Out of all these colorings, only two will be monochromatic, one with all edges red and one with all edges blue. Therefore, the probability that a randomly chosen kk subgraph is monochromatic is 2 over 2 to the k choose 2, which is equals to 2 to the 1 minus k choose 2. The graph Kn has n choose k subgraphs that are isomorphic to kk. Each of them has the same chance to be monochromatic. On the other hand, the probability that at least one of them is monochromatic is at most the sum of these n choose k individual probabilities by proposition 15.2. In other words, if AS denote the event that the kk subgraph S of G has monochromatic edges, then the probability of the unions of AS union for all possible S is less than or equals to the summations of the probability of AS summing for OS, which is equals to n choose k times 2 to the 1 minus k choose 2. So S ranges through all kk subgraphs of G. Now let us assume, in accordance with our criterion, that n is less than or equals to 2 to the k over 2. Then the last term of 15.1 can be bounded as follows. That is, n choose k times 2 to the 1 minus k choose 2, which is less than n to the k divided by k factorial. That's for the n choose k term, times 2 to the 1 minus k choose 2, which is less than or equals to 2 times 2 to the k squared over 2 divided by k factorial times 2 to the k choose 2, which is equals to 2 times 2 to the k over 2 divided by k factorial, which is less than 1 for all k which is greater than or equals to 3. The last inequality is very easy to prove, for example by induction. We have seen in chapter 13 that r of kk is less than or equals to 4 to the k. Our latest result shows that the square root of 2 to the k is less than r of kk. These are essentially the best known results on the size of r of kk. So there is a lot of progress to be made on Ramsey numbers. Theorem 15.6. Let n and m be two positive integers larger than 1. And let m is greater than or equals to 2 times log base 2 to the n. Then it is possible to color each edge of knn red or blue so that no kmn subgraph with monochromatic edges is formed. Proof: the number of ways to color the edges of a given kmn subgraph of knn is 2 to the n to the square, and two of these colorings result in monochromatic subgraphs. Therefore, the probability that at least one monochromatic kmn is formed is at most n choose m to the square times 2 to the 1 minus m squared. Therefore, all we have to prove is n choose m to the square times 2 to the 1 minus m squared, which is less than 1. That is 2 times n choose m to the square, which is less than 2 to the m squared. To see this, we insert two intermediate expressions as follows. 2 times n choose m to the square is less than n to the 2m, which is less than or equals to 2 to the m divided by 2 to the 2m, which is equals to 2 to the m squared, where the second inequality is a simple consequence of the relation between n and m. Another way to formulate this same theorem is as follows. If m is greater than or equals to 2 times log with base 2 of n, then there exists a matrix of size m by n whose entries are either 0 or 1 having no m by m minor that consists of zeros only or of ones only. What is amazing about this result is that nobody knows how to construct that matrix or how to color the edges of knn so that the requirements are fulfilled. In fact, the gap between what we can do and what we know is possible is rather large. The best construction known to this day for an m by m matrix with zeros and ones and not having m by m homogeneous minors works for m equals to c times the square root of n, where c is a constant. This is much more than what we know is true, that is m equals to 2 times log with base 2 to the n.